Thank you for the introduction, Josh. My name is Moo Sun, and I'm a PhD student from Professor Brass Group at the Department of Chemical Engineering. And thank you for providing me the chance to present on my research at this student research forum. And today I'll present about, oh, by the way, can everybody see the screen?
Yep.
So I'll today present about the digitalization of biopharmaceutical manufacturing. So I guess I'll have to start with giving a brief introduction of what the biopharmaceutical is. So they are the products derived from biological organisms for treating or preventing diseases. And as you can see in this graph, the global sales of biopharmaceuticals have been continuously increasing for many years. They are projected to reach about $500 billion by 2026. And also the percentage of biopharmaceuticals in the drug pipeline have been also continuously increasing. And this results in hundreds of approved products on the market and over 8,000 medicines in clinical development. So the figure in this slide shows a process flow diagram for a typical platform that is used for producing monoclonal antibodies. And monoclonal antibodies are the highest selling class of biopharmaceuticals. And this traditional biopharmaceutical manufacturing consists of a similar sequence of batch unit operations that are divided into the upstream and the downstream. So if we take a look, the upstream unit operations include the cell culture with a series of batch bioreactors, which is for the protein expression, and the harvest steps, which are for the removing cells and cell debris. And here it is centrifugation and filtration unit operations. And the downstream consists of purification with multiple steps of chromatography, as you see here and here and here, and also the filtrations and the diafiltrations unit operations. So there are several trends in the biopharmaceutical manufacturing, which is providing important roles for the process system engineering. So first, the growth of biologics increased the interest in applying process analytical technology, which is called PAT. So PAT is a system of analyzing manufacturing through online measurements of critical quality attributes, which is to ensure the final product quality. So online measurements provide much more data on the multivariable interactions and dynamics. And depending on the process understanding, these data have been used to construct first principles and database models for each of the unit operation in the system. And another trend is a transition of many processes from batch to continuous operation. And this is for reducing manufacturing costs and increasing productivity and quality. However, the continuous manufacturing processes also provide new process control problems. The continuous processes have to handle the propagation of impurities and other disturbances caused by the tight integration of those unit operations. And the another area of interest is the invention of new designs for the protein separations. So currently the dominant method is picked bed chromatography due to its high resolution, but this method is actually costly for the high dose pharmaceuticals. So non-chromatography separation methods are becoming more attractive as the modern bioreactors are achieving higher product titers. And the crystallization is one of the more promising proposed technology. And this will be a major shift in the biopharmaceutical manufacturing. It will involve new processes to be controlled. And these trends ultimately lead biomanufacturing to digital manufacturing. So digital manufacturing is an integrated approach to manufacturing that is centered around the computer system. And again, digital manufacturing is enhanced by using the modern systems engineering tools. First, modeling and simulation provides increased mechanistic fidelity and better empirical approaches. And it can be also applied real time for the automated decision making. And the process optimization can be also applied real time for drug and patient specific manufacturing. And high fidelity model-based optimization can also reduce experimental costs. And systems engineering also provides tools for dealing with process uncertainty and model-based optimal control. And these results in fully automated system, minimizing errors caused by the human operators. And the synergy between these tools enhances the impact to the digital manufacturing. And the figure on the slide shows the knowledge pyramid for model-based decision-making. The higher layers in the pyramid correspond to the greater knowledge, more informed and the better reliability of decision-making, and the lower requirements for the regulatory oversight. Because higher layers in the pyramid rely more on knowledge and expertise, they are more generalizable and extrapolatable. And this makes these models applicable for optimization and predictive scale-up. On the other hand, lower layers in the pyramid rely more on data, and they're more specific and limited to interpolation. So these models have limited predictive power beyond the training set. So my research topics deal with the challenges related to these recent trends in the biopharmaceutical manufacturing. They can be also divided into the upstream and the downstream. So for upstream, I've derived mechanistic mathematical models and the optimal control methods for the multiple bioreactor configurations, including the microbioreactor systems and the stir tank bioreactors. And for downstream, I designed and implemented laboratory systems for protein crystallization and the continuous Brown activation system. These systems were optimally designed and controlled based on the mechanistic mathematical models. In addition, I'm trying to combine these experimentally validated unit operations into a plant-wide dynamic model. And this integrated plant-wide model would be able to map the raw materials and operations to the product quality attributes anywhere in the process systems. And for today's talk, I'll be focusing on presenting the work on what I did for the continuous Brown activation system. So as I have already mentioned at the beginning, the continuous manufacturing has been of interest to both academia and industry. And this is because of the many advantages that it provides, such as like reduced cost, increased flexibility, easy standardization and scale up, and also the improvement in the product quality. However, the complexity of these processes also bring control challenges and opportunities. And as you can see from this typical process flow diagram, biologics derived from mammalian sources have to undergo two orthogonal virus removal processes. And this is to remove the adventitious viruses that might be present in the master cell bank. And one of the common processing steps is a batch low pH hold to inactivate the enveloped viruses. And there have been several attempts to adapt this technology to continuous processing, which includes the cyclic batch operation, continuous flow tubular reactors, and column-based reactors. However, none of these continuous flow reactors actually directly address the control challenges with operating the system. So for the system, critical process parameters are the operating pH and the residence time distribution. And these determine the viral clearance and also the impacts to the product quality from the over-incubation or excessive pH adjustment. To address these control challenges, we have constructed a low-cost column-based continuous Brown activation system with off-the-shelf components. So for operating pH, we have implemented a fast and accurate model-based feedback control to enable rapid startup and effective disturbance rejection. And for residence time distribution, it was estimated periodically during operation through inverse tracer experiments. Then this was used to estimate the minimum residence time, which in turn was used to adjust the feed flow rate to maintain the residence time distribution. So to look into the constructed system in more detail, the figure in this slide shows a process flow diagram of the lab scale continuous Brown activation system. So if we take a look from left to right, first, to bring the fluid to a low pH state, a multi-channel peristaltic pump was used to pump the input solution and acid to a mixing unit and an inline pH electrode. Then the mixed stream then flowed into a column packed with inert glass to incubate low pH solution for sufficient time for Brown activation. An injection system was used to periodically inject UV transparent solution into the flow stream, and the UV absorbance sensors were placed at the column inlet and outlet to measure the column transit. Then the pH of the fluid leaving the column was raised by mixing with base using a second mixing unit and the pH electrode. And the programmable logic controller was used for the low-level control of the overall system. Measurement data were received from the pH and the UV sensors, and the multi-channel peristaltic pump was connected for the control actuation. And the programmable logic controller was also connected to computer for data collection, human-machine interface, and the online parameter estimation. And to start with modeling and control of pH, fast and accurate control is necessary for the rapid inactivation while minimizing the impact to the product quality.
Sorry, Moo-san, can I interrupt you for a second?
Oh, sure.
I forget this one simple fact. So I think you said, so you're concerned about the product being held for enough time in the low pH holds, right? Is there an issue if you hold it for too much time?
Also, that's actually a very good point. So we are actually introducing the low pH to actually inactivate the enveloped viruses, right? But
Right.
actually the protein of interest, also biopharmaceuticals in this case, are also actually affected in terms of quality by the pH as well. So
Okay,
if
that's
it
what
is
I thought.
actually maintained for too long time in the low pH, it might lose its activity or it might actually be lies by the low conditions. So it's also important to just maintain it for the specific amount of time that you want for the inactivation.
Okay.
So the overall goal is to actually maintain the correct pH for correct amount of time in the
Okay,
system.
I see. All right. So you have balance on both sides.
Yes, we have balance on both sides. So like
Okay.
balance or like set point for both sides, yes.
Okay.
And how we determine is just from the many screening tests that people actually perform to get the knowledge about the inactivation kinetics and also the protein stability kinetics.
Okay. How much does that change based on the product?
Actually, so the monoclonal antibody is what we consider for our project. And monoclonal antibodies are actually very similar in structure, even between different products. So they are actually pretty consistent. But if
Okay.
we actually want to consider the another class of biopharmaceutical, they might be very different due to their structure of the protein.
Okay. Okay.
Actually, sorry,
Uh,
go.
just real quick, you mentioned that inverse tracer step where you're trying to characterize residence time. So was that an engineering effort to try to estimate parameters, or is that an online thing to try to online measure residence time?
So actually, that's also a very good question. So I will explain more in detail as the talk proceeds, but just to give you a quick answer. Also, since we want to actually maintain the specific residence time in the system, we want to actually check at each of the time point if what is the actual residence time distribution on the system because of the disturbances that might be introduced in the system, like column fouling. Even with the same operating condition, the residence time distribution can be changed throughout the operation. So we use the inverse tracer experiments to actually estimate the residence time distribution at each of the time point and use that information to adjust the free flow rate to maintain the residence time at what we want as a set.
And then by residence time distribution, do you mean the variation in residence times that happens during the operation of the system, kind of long term?
Yes, because like what I have explained before, we want to actually have this low P solution to be remaining for a certain amount of time, not too long, not too short. So actually, the residence time distribution throughout the column in the low P state is what we are actually interested in the system. We want to actually make that residence time distribution less dispersed and like very controlled at specific time.
Gotcha. So that's your main, or what you're trying to affect overall.
Yeah, so that's the overall goal of the system so that we actually have the accurate low pH to be maintained for the accurate amount of time.
Gotcha. Thanks.
Yes, thank you for all the questions. And so now actually we can actually look into how the models are constructed and how the controllers are constructed based on those models. So if we actually first take a look at the pH, so fast and accurate control is necessary for rapid activation while minimizing the impact to the product quality. So for this, what we have done is we have constructed the first principles pH model with a reaction invariance, which are the total concentration of acid-base species and the total charge of the remaining species. And to give you a little bit of a chemical engineering background, the basis of the pH model is from the acid-base equilibria and total charge balances, which are the functions of the reaction invariance and the acid dissociation constants. And what we do with this developed pH model is that we have implemented a PI controller that is based on the reaction invariance instead of pH, which are now governed by the linear dynamics. And this actually accounts for the nonlinearities in directly controlling pH. And this, you will know from the typical buffer titration curve that it is actually a big problem. And the uncertainties that may be existing in the pH model were handled by the maximum a posteriori MAB estimation. So what this does is this updates the primary values based on the online measurement data. So the MAP estimation was formulated as a constraint minimization problem at each of the time points. And it takes into account the prior information of the primaries and the current data to provide the improved estimates of the primaries at each of the time points. And estimated model parameters were the acid dissociation constants and also this term alpha that you see in this equation. And term alpha was used as a multiplicative factor for correcting the reaction invariance to deal with a flow bias in the feed stream. And the covariance of the posterior distribution was also updated at each of the time point with the sensitivities of pH with respect to the estimated parameters. So this MAP estimation addresses the uncertainties due to the natural or unexpected variation during the operation, such as changing product and the buffer concentration in the system. So this improves the performance and the robustness of the reaction invariant pH controller.
Moo Sun, is that a typical strategy in like a chemical engineering control problem, or is this something that was totally new that you guys created?
So the idea of so for the model predictive control, the idea of having the primary adaptation is pretty common because as you know, like the models are not always perfect. So if we actually learn more as we obtain data, it's very useful. But the way of how you obtain the primary adaptation is different work by work. So I think the more common method that you might be familiar with can be the Kalman filter or extended Kalman filter. But the MAP estimation is what we have applied for this specific application.
Yeah, the plant I worked in, we did pH balancing and we did like a strapping table. So given a current pH, we kind of knew how much dose we need to get into the range we wanted to, and then use a PID controller to fine tune it. But I think tons of people have their own opinions on the best way to do pH control in practice.
You said that this is a constrained minimization problem that you're trying to solve. Is there a closed form solution to it, or does it end up being a linear programming problem, or is there some other solution to solving?
So that's a very good question. So it doesn't really have a predefined form of analytical solution. So we solve it numerically at each of the time point. So this is one of the reasons why that we had the programmable logic controller connected to the computer in the system, because the reason why we use the PLC or the low-level control is that it's very, very stable, and so it's industry standard. So it will never fail during the run. But because of its simplicity, it doesn't have the computation power to perform like optimization in each of the time. So for that, we use the computer for the actual optimization or the primary estimation, but we feed the information back to the PLC. So the PLC actually performs the optimal control at each of the time.
Got it. And so when you solve this optimization problem, is it just like a gradient descent solution, or how is that done?
So the optimization algorithm that we have used is a gradient descent.
Okay.
And it's actually so because the size of the model equation is not that large, it is actually computable within a second, which is the time period that we use for the computer computation. But the PLC actually runs very fast in the cycle of like a millisecond.
Cool,
so
thanks.
Do you have like your regulatory PID box? Well, I guess, are you just using on-off control for the pumps?
No, actually it is a PI control, and how we actually implement in the PLC controller is we just use math boxes to have this error term, the integrator term, and then just calculate what the control input is going to be and give it the actual control input value to the pump by the connection with the PLC and the pump.
So is the computer providing the set point to those controllers that are executing on the PLC?
So for changing the set points, we would actually give the command to the computer, then computer will talk to the PLC to change the set point, but actually doing the PI control is actually implemented in the PLC itself. Gotcha. The computer only interacts when it actually has to update the primary values based on these primary estimation, or if you want to change the set point of the operations. So computer is used for the primary estimation and also the human machine interface.
Gotcha. Okay.
Cool. So now let's move on to the low pH hold part. So the column-based inactivation reactors have to be designed to simultaneously balance the competing objectives of what you see here, the design throughput, residence time, low pressure drop, and small dispersion. This is all required to actually have the very specific residence time that we want in the system operation. And what we have for the design variables are the column diameter and column length, and the particle size and the superficial velocity. And for the column-based design, throughput is scalable to the diameter of the column, so this variable is not independently adjustable in the system. And having a fixed average residence time also relates the column length and the superficial velocity, but we can also consider the column length to be fixed as well. Then the pressure drop from the Karman-Kosen equation can be reduced to the given formulation that you see in the slide. In a similar way, the standard deviation of a dispersed peak can be characterized as a given formulation from the correlation of the dispersion coefficient. And we can actually see in these both relationships that the terms of superficial velocity over particle size only appears together in these formulations. But we can actually see that there is no way to optimize a choice of particle size or superficial velocity to simultaneously reduce the pressure drop and the dispersion at the same time. So in the interest of system compactness, we usually use the small particle size and the superficial velocity for the system design. And the quantitative understanding of the low pH hold is important to balance the two competing effects of the Brown activation and the degrading product quality. And this comes in the form of the residence time distribution, which means that the time that a fluid element spends within the system by the probability distribution function. And here we model the column as the plug flow reactor with axial dispersion in series with a continuously stirred tank reactor. And their respective residence time distributions are shown in the given formulations. So the plug flow reactor with axial dispersion describes a cylindrical chemical reactor with continuous flow, and the continuously stirred tank reactor describes any non-ideality that might be present in the actual column operation. Then the concentration at the outlet of the column can be calculated through the convolution of the concentration at the inlet and the residence time distribution of the column. And again, the residence time distribution of the column can be calculated through the convolution of already modeled residence time distribution of plug flow reactor with axial dispersion and the continuously stirred tank reactor. And the cumulative distribution function can be also simply computed by integrating the residence time distribution over time. And this allows us to define the minimum residence time as the given formulation. And the term eta here is a small value corresponding to the fraction of material leaving the column before the defined minimum residence time. And this residence time distribution is affected by the several variables such as the reactor design, geometry, fouling, and the input flow rate. And these variables can be classified into three different types. So design variables are those that can be controlled offline, like the reactor design and the geometry. And disturbances are those that may vary during operation, but cannot be effectively controlled, like column fouling. And the manipulated variables are those that can be controlled online, like the input flow rates. And while design variables have been explored quite extensively by previous work, the disturbance rejection has not been discussed directly in those works. Actually, the disturbance rejection is even more important, as these continuous reactors will be operated for extended period of time in the pilot or commercial scale of the system. And because the residence time distribution is infinite dimensional, it is impossible to completely reject a disturbance with a scalar manipulated variables. So this has to be done on a scalarization of the residence time distribution. One of the scalarization is a logarithmic reduction value approach, where a nonlinear model is used to relate the residence time distribution to the scalar logarithm reduction value. And this approach directly addresses the critical quality attribute, but relies on an accurate inactivation model. However, inactivation kinetics vary from virus to virus, and they are uncertain during the process development stage. So we avoided this uncertainty by utilizing the minimum residence time approach instead. So the fraction used for defining minimum residence time varies from 0.005 to 10 to the minus 5 in the literature, and we used 0.005 fraction for this work. At the same time, I would like to mention that the different fraction or even logarithmic reduction value approach can be trivially implemented with information of inactivation kinetics. So for controlling the minimum residence time, three components are needed for the system. First, the means of measuring the residence time distribution in minimum residence time. Second, feedback control algorithm for adjusting the flow rate in response to the minimum residence time measurements. And lastly, means of actuating the flow rate. So first, measuring minimum residence time directly using tracer experiments is impossible due to the small fraction value and inline sensor noise. So to overcome this lack of observability, residence time distribution was estimated as a primary distribution, which then can be used to determine the minimum residence time. And using the Beard-Lambert law, the absorbance that we measure is directly proportional to the concentration. So the parameters for the residence time distribution model can be calculated through the given sum of squares minimization problem. And as you can see, the sufficient variability is necessary in the inlet absorbance for the accurate parameter estimation. And this can be achieved through the normal process variation in the system, but it can be also achieved safely through the periodic injection of protein-free buffer, which has negligible UV absorbance.
Sorry, Moo Sun, can you go back for a second?
Yep.
So how easy is it to solve that equation over all of those parameters simultaneously?
So actually, all the optimization that I present today are all achievable within the time period of the computer connection with the PLC, which means it's all within the second.
Okay.
And also, for unlike the pH parameter adaptation, this only happens when we actually have the injection of water. If you
Right.
So this only happens once in a while, but the computation of this object optimization is also pretty fast. Again,
Okay.
it doesn't have a analytical form of the solution. It's solved numerically by the gradient descent method, and all the optimization is performed in the MATLAB in the computer, and it simply uses the basic optimization function given in the toolbox.
Okay.
Yep. So after having this minimum residence time measurement, now the feedback control algorithm is developed, as you can see in this given formulation. And because peristaltic pump flow rates are almost linear to the pump rotational speed, the system can attain set point with a single step after the residence time distribution measurement, as you will see soon in the experimental results. And any nonlinearities or the disturbances, such as a tubing stretch that will happen for the long period of operation, are also addressed through this feedback control. Now, so for the experimental validation of the system that I described, we have conducted experiments to demonstrate the controller performance. And these experiments were planned to ensure that the first solution pH is correctly low to the target pH for violent activation, and then the solution residence time is accurately and precisely controlled, and the solution pH is raised back to the target pH for the further down unit for further downstream unit operations. So first experiment was planned to demonstrate that the system is capable of tracking the pH and the minimum residence time set points. And the second experiment was planned to demonstrate that the system is capable of suppressing the pH disturbances. And this was done by changing to a different buffer for pH control without updating the initial parameter values in the model. The last experiment was planned to demonstrate that the system is capable of suppressing residence time disturbances. This was done by using a bypass line to suddenly decrease the active volume in the system and see how the system responds. And for these controller validation experiments, we used the 0.1 molar sodium hydroxide as a test input solution with 1% acetone used as a tracer for the absorbance measurement. And the 1 molar phosphoric acid was used for the acid stream, and the 1 molar sodium hydroxide was used for the base stream. And the deionized water was used as a low absorbance injection solution for the residence time distribution estimation. So plots on this slide shows experimental results for tracking pH set points. Plot on the left shows flow rates determined by the pH controller, and plot on the right shows the pH measurements with set points shown as black dashed lines. And as you can see in the plot on the right, during the experiment, pH set point for the first mixing unit was changed from 3 to 4 at 60 minutes and reverted to 3 at 120 minutes. And the pH set point for the second mixing unit was also changed from 7 to 8 at 180 minutes and reverted to 7 at 240 minutes. And we can see from this plot that the set point tracking was achieved with fast and accurate response and no instability. And plots on this slide show the experimental results for tracking minimum residence time set points. Plots from the top show flow rates determined by the minimum residence time controller, absorbance measurements at the inlet and outlet of the column, and estimated minimum residence time with set points shown as black dashed lines. And as you can see in the bottom plot, during the experiment, minimum residence time set point was changed from 240 seconds to 300 seconds at 180 minutes, and reverted to 240 seconds at 360 minutes. And first, we can see from the second plot that the residence time distribution model with estimated parameters will describe the concentration at the outlet with the information given of the concentration at the inlet. And also, we can see from the bottom plot that the set point tracking was achieved within a single step after the residence time distribution estimation. And moving on to the next validation experiment, the disturbance rejection was tested for pH control by changing the buffer of the acid stream from the phosphoric acid to the citric acid. And this was done with the model being still initialized with the acid dissociation constants of the phosphoric acid. So model is initially not aware of the buffer change in the acid stream. And plots on this slide show the experimental results for the disturbance rejection of pH controller. And from the top, plots show flow rates determined by the pH controller, pH measurements with set points shown as black dashed lines, and the estimated primary values of acid dissociation constants with the true values for citric acid shown as a black dashed lines. And we can see from the second plot that the set point tracking was again achieved with fast and accurate response and no instability, even with the introduced disturbance. And we can see from the bottom plot that the MAP estimation algorithm correctly estimates the acid dissociation constants of citric acid purely from the pH measurements in the first few minutes. And for the last validation experiment, disturbance rejection was tested for the minimum residence time control by adding an additional length of tubing in series with the column. And while the system is in normal operation, the tube clamps were used to remove this additional length of tubing in the flow path as shown in the process flow diagram. And this effectively led to suddenly decreasing the active volume through the column, and therefore suddenly decreasing the residence time in the system. And the plots in this slide shows experimental results for disturbance rejection of minimum residence time controller. Red vertical line shows a time when the length of the tube was decreased with the tube clamps. And we can see from the second plot that the model correctly predicted the output of each water injection, even after when the sudden disturbance was introduced into the system. And we can also see from the bottom plot that the minimum residence time measurement correctly identified the sudden change in the system residence time. And the controller adjusted the pump speed accordingly and restored the original residence time set point again in a single step. So for conclusion, in this work, we have constructed a low-cost column-based continuous funnel activation system with the off-the-shelf components. And the controller validation experiments demonstrated that the pH and the minimum residence time set point tracking, also disturbance rejection, are achieved with fast and accurate response and the no instability. So overall, this work provided tools for the design and operation of continuous final activation systems in service of increasing productivity, improving product quality, and enhancing patient safety. And I would like to acknowledge my coworkers listed here for this work, and also the funding source, US FDA. And thank you all for your attention, and I'll be happy to answer any other questions.